Of course, our approximation was only an approximation. How can we get the accurate moment of inertia for a disk of radius r and mass m, a uniform disk of this radius and this mass? Well, it turns out we're going to have to use calculus. The reason is because the contribution of each little ring to this disk depends on the square of its distance from the center, whereas its mass is only proportional to the first power of that distance. And any averaging we can do is going to be imprecise unless we first use calculus or stumble upon the right way of averaging the radius of a disk. We saw that before we couldn't simply collapse each ring to a ring of its average radius because we have more mass outside of the average radius than we have inside the average radius. For a lot of reasons of that nature, we just have to go to calculus. So if you're now you'll be able to follow the first couple of steps here. There's just one little step here that involves calculus. So follow along and let's see what we've got. If we look at a typical ring of this disk, a ring whose radius is r, and we don't really care whether that r is to the inside or the outside or the middle or any point inside the ring. It's just a thin ring of radius r and thickness delta r. Now, mathematicians, and I'm actually a mathematician as much as a physicist, if not, well, probably a lot more, but mathematicians do worry about where this r is and worry about errors in the approximation. Physicists usually just kind of slop over these things a little bit and don't worry too much about the foundations of the mathematics, although they do very precise mathematics better than a lot of mathematicians do. But we're going to follow the physics approach, so we don't really care where that r goes. Now, what we want to know is what's the moment of inertia of this little ring. To find the moment of inertia, we'd better find the mass of the little ring. It's got a radius r, a thickness delta r. We ask ourselves, if we took this thing and cut it out, and then snipped it here, and then kind of grabbed it by the ends and straightened it out, what would we end up with? Well, when we straighten it out, it's going to have a length that's equal to the circumference of this ring, and a thickness that's still delta r. So we're going to end up with something very much like this. A length very close to 2 delta r and a thickness of delta r. Now at one end the cut's actually not going to come out straight. If it comes out straight at one end, it's not going to be straight at the other. And it's not exactly 2 pi r. But as delta r gets smaller and smaller, that little angle at one of those ends becomes less and less significant and won't really have any effect when we do the calculus, which involves taking the limit as our delta r goes to 0 of the sum of all these things. In any case, the area of this thing, this is clearly very close to a rectangle, 2 pi r by delta r. The area is going to be about length times width, 2 pi r delta r. The mass in this thing is going to be what? Well, it's got area 2 pi r delta r. The area of the entire disk is pi r squared. So if we take the proportionality here, this ring here that's been straightened out in this picture will have a mass that's in the same proportion to the area as the area proportions. So we take the area proportion, 2 pi r delta r over pi r squared, and that's the proportion of the total area that's in here, and that's going to be the proportion of the total mass, so that to get the mass contribution delta m, we simply multiply this proportion by the mass. Now everybody should follow that much. The next step is, of course, the calculus step. And if you don't know calculus, you're not going to understand the step. If you do, the step should be fairly straightforward and fairly easy. The moment of inertia is what we get when we add up all the delta m's times r squared. Okay? Now, when we add up all our delta m times r squareds from this expression and take the limit as our delta m's go to 0 or as our delta r's go to 0, we get the integral from 0 to r of 2 pi r dr over pi big R squared times m times little r squared. Now everything in here is a constant. We bring out the pi's divide out. We bring out the 2 and the big R squared and the big M right here, and then we integrate from 0 to R, the R here times the R squared here, which is R cubed, times dr. And that integral is real simple. The integral comes out R to the 4th, big R to the 4th over 4, and we end up with mr squared over 2 for the total moment of inertia. So by finding the area of this little strip here and getting the mass contribution of the little strip, then taking the limit where delta R becomes a dr, and summing it from radius 0 out to the outer radius of the disk, we get this expression. And of course this is the accurate moment of inertia of an ideal disk of radius r, mass m.